my name is Jamie Thomson. I am an engineer for a company called dunnhumby in the UK. We're a big GCP customer, and we've been using Dataproc for a couple of years now. So really, today's session could be retitled Our Journey with Google Cloud Platform. I'm going to talk a lot about what we've been using, how we do a lot of the stuff that we do, especially using Dataproc. And I'm quite lucky because I'm here representing the team that I work for, which within dunnhumby is a team called Core Technology. It's our job to provide infrastructure and services to the rest of the company. A bunch of very smart people, and I'm lucky enough to be here representing that team of about 25 people today. So what do dunnhumby do exactly? I want to just level set so people understand what it is we do, because that will feed into the rest of the presentation. So we're a customer-first data science company, and we believe that if our clients put their customers first, then through that they can drive loyalty, through that they can drive long-term sustainable profit. We've been doing this for about 25 years now, long before the term big data had ever been coined, and we're wholly owned by Tesco in the UK, and they're also our biggest client, and we've been behind the success of Tesco's Club Card loyalty scheme for some years now. So at a high level, we do a couple of things for our clients. So firstly, we provide consultancy over the data that they provide to us. Clients will ask us tactical questions like, why am I losing very price-sensitive customers to my competitor? Or they'll ask us strategic questions, such as, what would be my best media strategy for return on investment over the next 4 to 5 years? And in both of these cases, we try and answer those questions through a combination of data and data science. Over the past 25 years, we've had a lot of experience, and as you can imagine, we come across some common problems quite a lot. We built up a software portfolio to address some of these issues. So we have products around category management, pricing promotions, and media. So we have a category assortment offering, which helps typically our retail clients decide what to put on the shelves. Our media offering helps our clients decide who to target with offers and when to do that. And pricing promotions helps our clients make decisions such as what promotions should I be putting on in my stores in the next couple of months, things like that. So this short slide covers where we work. So we're all over the globe. We've got 78 retail clients and over 1,000 consumer packaged goods clients. We manage data for about 800 customers of our retailers. And we've got a data corpus of about 44 billion baskets that our data scientists work against every day. So just want to go in a nutshell what dunnhumby kind of do and how we work. So clients will send their data to us. And when they do that, we will assign a team of data engineers to that client, and it's their responsibility to take that incoming data, transform it into what we call a common data model that can then be used by our products and by our services, by our data scientists throughout the company. So that's the role of our data engineers. We have products which consume that common data model, and we have data scientists which provide consultancy services running algorithms over that common data model. And finally, we deliver services back to our clients in the way of APIs and data visualizations. So I said we've been in this business for about 25 years, but our business has been changing over the past 5 years. We typically sought very long, multi-year engagements with our clients, but we were finding that was becoming really unpalatable to a lot of our prospects. Clients really wanted shorter engagements with us, and they were looking for a lot more flexibility of how we can actually provide what we provide. Our technology stack was very proprietary. It was best of breed, which is another word for saying it was very expensive. And we hosted all of our own infrastructure as well. So we have 4 data centers, 2 in the US, 2 in the UK, and we've got about 4 petabytes of data stored across those data centers. So we made a conscious decision to move to open source and cloud. Open source because it was cheaper, much more flexibility, and cloud because buying hardware for short client engagements was never really going to be feasible for us. So we're about halfway through our journey of migrating all our clients to the cloud, and we hope to, in a couple of years, fully deprecate all of our data centers. The technology stack that we're using is what I put on the slide here. So we were using Oracle Exadata for storage, SAS for data processing, and Redwood Chronicle as our scheduling tool. All three of which, best of breed, very expensive, and they cost us a lot of money. So through a program of work which we call Tech Renewal, we made a lot of changes to how we deliver stuff and the tools that we use to actually deliver it. So we made a big investment in Python as our chosen language for our data scientists. We made a big bet on Apache Spark. We adopted Spark when it was around the 1.6 version. I think since then it's proved to be the kind of de facto tool for big data processing. So we're very pleased with what Spark's doing for us. We've adopted Apache Airflow as a workflow tool. For those that don't know, this is a scheduling workflow tool that came out of Airbnb. And we use Jupyter Notebooks. Our data scientists use Jupyter Notebooks. We provide them to us as part of the infrastructure that I'm going to demonstrate today. And we made a big bet on Terraform as well. Terraform is a tool from a company called HashiCorp. And what it does is allow you to manage your infrastructure as code. So we're using that to deploy everything that we're going to be talking about today. And I've got a demo a little bit later that will talk a little bit about that. We're using Grafana, another open source tool for visualizing monitoring data. And finally, the other big bet that we made was choosing GCP as our preferred cloud provider. And as part of that, Dataproc has become the cornerstone of everything that we're doing on GCP. And we've been using that for about 2 years now. So Tech Renewal is providing dunnhumby with quite a lot of benefits. We now have a modern tech stack, the things I was just talking about. Massive reduction in cost, basically through the we don't have to pay license fees anymore. Better provisioning, we can provision infrastructure for new clients a lot quicker than we can ever do that in the past. Much more scalable platform, we can dial it up and dial it down as we need. We have a lot more hosting options. Previously, all we could do was host clients in the US or the UK. We can now host them wherever Google have got a data center. Much more robust security. We build on top of Google's investments in that area, and we benefit from that. And we're also finding a lot more opportunities from this as well. There's a lot more clients out there who want to be on the cloud and want to come on this journey with us, and it's providing a lot more partnering opportunities for us as well. Okay, so that's enough spiel about what dunnhumby actually do, what we are. I want to talk more now about the real meat of what we're doing, and this is something that we call transient Dataproc clusters. Google refer to it as ephemeral Dataproc clusters. I don't know why we called it something different, but transient data clusters is how we refer to it internally. Basically, it means when we're not using Dataproc, we turn it off. That's a very simple premise, and this presentation really talks about how we do that. So there is a blog post, the link at the bottom, which is from Google, that explains exactly how to do this. So a flexible way to deploy Hive on Cloud Dataproc. And the way it works is you can imagine you might have multiple clients that actually want to use Hive running upon Dataproc. So that might be Spark clients, it might be MapReduce clients. So in this diagram here, you'll see we have two of these transient clusters, or ephemeral clusters, as Google call them. I took this diagram from the blog post, actually. And each of those clusters is running Hive, Hive metastore service, and it runs a component called Cloud SQL Proxy, which is a Google-provided component that allows the Hive service running on that ephemeral cluster to connect to a Hive metastore. And that Hive metastore is running in Cloud SQL, Google's Cloud SQL offering, and specifically we use MySQL. The data itself that we process and we store is stored in Google Cloud Storage, in storage buckets. We don't store the data on the cluster itself, because as I was saying, when we're not using those clusters, we want to get rid of them. Obviously, we need the data to persist, so we use Google Cloud Storage buckets in order to do that. So we offer transient clusters for both of those types of groups of users that we talked about before, so our data engineers and data scientists. We group all the things that we deploy into components. We have a component that we call Data Platform. This specifically is what I work on. And what we provide to our data engineers are these short-lived clusters. So clusters that you spin up to do a specific piece of work, and then you shut down when you're not using it. The way we do that is we allow our data engineers to provision clusters via a series of custom Airflow operators that we wrote ourselves. So our data engineers use Airflow as an interface to create these clusters and create their ETL jobs and then shut the clusters down. By using clusters for a single use, for a single job, that provides a great advantage to us because we can actually label those cluster resources according to what they are actually going to be used for. Okay, so a data engineer might be doing some work around dimension processing or transaction aggregation or feature generation, something like that. And if we can label what that cluster is actually used for, we can actually get fine-grained cost analysis of how much it actually costs us to carry out those functions, and you'll see that a little bit later. Finally, we use a feature called scheduled deletion. This is something that Google provide. It's an option when you create a Dataproc cluster that allows you to specify an amount of time that the cluster should be idle for before Google will automatically shut it down for you, which is really handy. Typically, we set this to 30 minutes. I think the minimum time you can set it to is 10 minutes. But basically, as soon as the cluster is idle and it's not being used anymore, Google will shut that down on our behalf. And the way they do that, so this is the command to actually create a cluster, and there is an option which is max idle. You set that to whatever duration you need, and it will shut it down for you when it's not being used. You'll see it's in beta at the moment. It's been in beta for quite a long time, but if anyone went to the session yesterday, Chris Crosby's session, somebody asked about this, and they basically said, yes, it's effectively been GA for a long time. They just haven't got around to switching off the beta tag yet. But it's there. We've been using it for a long time, and it's been very successful for us. OK, so that was talking about the clusters that we provide to our data engineers. Now I'll talk a little bit about our data scientists. Now, they have a slightly different need to our data engineers. They will need to carry out ad hoc analyses, and for that reason, we always need to have clusters available for them to do their work. It takes 2 or 3 minutes to spin up a Dataproc cluster, so what we never want to do is leave our data scientists sitting around waiting for a cluster to spin up. We need to give them much more immediate access to that. So what we provide for them is auto-scaling clusters. These are clusters that will increase, where the number of nodes will increase as the load on those clusters increases. So the more users that are using it, the bigger those clusters will get. I'll talk a little bit on the next slide about how we actually do that. We also offer Jupyter. So every single one of our data scientists has the ability to visit a portal that we provide and spin up their own dedicated Jupyter notebook running inside a Kubernetes pod that we manage on their behalf. So there's no need for a data scientist to install anything on their machine. We provide it for them. All they need is a browser that will enable them to use Jupyter. And of course, within Jupyter, that offers Python and R, so our data scientists have the option of using Python or R for the stuff that they're doing. OK, so a slide specific to auto-scaling clusters. So you may be aware that Google have got a feature, I think it's in beta at the moment, an auto-scaling feature. We're not actually using that. We actually built our own tool, which we call Tidebell, which will actually provide auto-scaling for us. And the way it works is it monitors cluster utilization via the Yarn API that every cluster has. And if it notices that memory pressure is getting above a certain threshold, it will start to add more nodes into that cluster dynamically. It uses preemptible nodes to do that. What are preemptible nodes? Well, Dataproc is built upon Google's Compute Engine service, and they've got an offering in Compute Engine called preemptible machines. And what they are they're standard VMs. However, they allow Google, when they need data center capacity, to take that away from what they're being used for. So that Google will actually take those down away from us with about a 5-minute warning. But that means they're really well scheduled to systems which are resilient to clusters going away, and Spark is really resilient to that. So it's great for us to use these preemptible nodes. The main benefit is obviously they're a heck of a lot cheaper. So I saw on the slide yesterday, from the Dataproc team that you can get up to 80% cost savings just through using preemptible nodes. So that's pretty much why we use them. We do expect to replace Tibel in the fairly near future with Dataproc's own auto-scaling feature. That's currently in beta. And aside from that, I think last week they also announced a new feature, which is currently in alpha, which is called Enhanced Flexible Mode, I think it is, EFM. And what that will allow you to do is make it a lot easier to use preemptible nodes, because what it actually does is persist the state of the jobs to HDFS before those nodes actually get shut down. So it's a really, we do have some issues with preemptible nodes. Obviously, if a node's going away when a job is running, that's not great. But this new EFM feature should be really valuable for us. And I can see Michaela in the back nodding, so I think if you want to know anything about it, Michaela in the back knows a lot more about it than I do. Okay, so I said we use Grafana for visualizing monitoring data, and this is a screenshot from Grafana. So this shows activity across our whole estate, across our Dataproc estate, pardon me, over a 24-hour period. What we're looking at here is the blue line is the number of nodes that we actually have active on Dataproc at a particular point in time. So you see when we actually took this screenshot, we had 105 nodes currently active at that time. The yellow line is the number of primary workers. That means the non-preemptible nodes that we have running. And the red shade there at the bottom is the number of preemptions that actually occur. So this is the number of times in a day that Google will take compute resources away from us. Okay, so just want to talk a little bit about how our data scientists actually work on this infrastructure. So typically, a data scientist will require the ability to do ad hoc analysis, so carrying out investigations upon the data that we provide in that common data model that I talked about earlier. They'll do that upon our auto-scaling clusters, because that's actually why we provide them. That's their reason for existence. And we also encourage our data scientists to use sample data sets rather than full data sets for doing exploratory work, for model training and things like that. The reason being that if they're using full data sets, A, it's going to cost us more because we're going to be spinning up more nodes to do it. And we do have a danger that if many data scientists are using a cluster at any one time, it is possible for a particular job to max out that cluster. And that will impact anybody else using it. So we do encourage them to use sample data sets wherever possible. So when they've done that, they've done a lot of work, they've decided on some work that they need to do. We will then encourage them to take that work that they've done in Jupyter and produce and turn that into a job that can be run on one of the short-lived clusters that I talked about earlier. So the difference between our short-lived clusters, which have the scheduled deletion option, and our long-lived clusters that use auto-scaling. So they use the auto-scaling clusters for investigation, and they'll run production-ready jobs upon our short-lived clusters. So what we're looking at here is a report that we built in Google Data Studio. So this sits on top of our billing data that Google provides to us, and that billing data is stored in BigQuery. So the number of things I just want to draw your attention to here. When we actually use these Dataproc clusters, we use labeling upon those clusters to tell us various things about what they're going to be used for. So for example, the data, we can slice and dice this data by the client that the cluster is being used for, because every cluster is dedicated to a particular client. The project that it's being used in, the components. Now, what do I mean by component? So I talked earlier about how we have our data platform component that we offer to data engineers. We have our analyst platform that we offer to data scientists. So we can slice and dice the data by those two things. We can filter, slice and dice by the machine type and the number of nodes. So this is really useful because we can actually see, we allow our data engineers to know the cost of actually running specific jobs. And if they can test that using different node configurations and see whether it's cost effective or not to actually use more nodes in their cluster. And finally, this is a real useful part of it. what we've allowed people to do is label the specific workload that they're using that cluster for. So as I talked about before, a data engineer might be doing things like dimension processing or transaction aggregation or feature generation. And if they actually label that cluster, and we give them tools to actually do that, we can actually get very specific costings about how much it costs to actually run that job. So you see in this example, I'm filtering on, I used the word workload over workload earlier. We actually call it a purpose. So we're filtering on a purpose of smoke test. So this is a test that we run across our whole estate. What it does, it's very simple. It spins up a Dataproc cluster, it runs some jobs upon it, and then it shuts the cluster down after. So we can actually get a cost for how much it costs us to actually run one of those smoke tests. So there's an example here. You can see it actually costs us 18 cents every time, well, roughly 18 cents, every time we spin up a cluster, run a couple of jobs, and shut it down. So that sort of fine-grained analysis is fantastic for us. We can never do that when we're running Hadoop in our own data center because it was shared between multiple clients, multiple engineers. Here, we're actually having single-use clusters, and we can actually get the cost of spinning one of those up, which is really advantageous for us. And you can see over the past few months, if you look in the bottom right-hand corner, that's cost us about $142 over the past 5 months, just running that particular smoke test. Okay, so in a single day, what do we actually do? So if we look at the lower numbers, first of all, we run these services for 35 clients currently. That's about half of our client base. I said we're about halfway through our cloud migration. So we've got about 35 clients running in GCP and approximately 300 terabytes stored for those clients. On any particular day, we use about 17,000 hours of compute engine time. Now, a particular hour is using a core in a compute engine instance for 1 hour. So 17,000 plus hours in any particular day. Thanks to our auto-scaling feature and thanks to our short-lived clusters, which we encourage our data engineers to spin up as and when they need, we actually, on the particular day we measured this, we created 2,971 nodes. That's virtual machines running in compute engine being used for the purposes of Dataproc. 525 of them got preempted. So that gives you some sort of indication about the preemption rates that we're seeing from using preemptible nodes on our Dataproc clusters, on our auto-scaled clusters. So that whole lot, 17,000 hours, costs us approximately $7,600 a day. I'll let you figure out whether that's expensive or not. We're pretty happy with what that's costing us because, as I say, that cost is spread across those 35 clients. And we have approximately 175 data scientists on any particular day using Jupyter on our short-lived clusters, accessing that data that's sitting in Google storage buckets. So this is the money slide in more ways than one. This depicts the cost of actually providing the services that we provide to just one single client over a 12-month period. So I didn't include the y-axis because the numbers themselves are not that important, but I think you see the profile is what I really want to draw your attention to. And you'll see in August last year, we had a huge downturn in the actual expenditure of cost to serve this client. And the reason for that is very simply, that's when we introduced transient clusters for this client. So a very real depiction of the cost saving that we're getting from using transient clusters. The spiky workloads that you see over to the right-hand side that have increased over the past 3 or 4 months, that's because our analysts, our data scientists, now getting much more familiar with the platform, and they're starting to run much more production-ready workloads on this. And it's spiky because we're encouraging to use those short-lived clusters that I talked about earlier on. So, a lot of people ask us, okay, that's great, you're using Dataproc for things like that. Seems to be pretty successful, but you're on GCP, why not just use BigQuery? And I've had a lot of people from Google asking me the same thing this week as well. So there's a few reasons. GCP is our preferred cloud provider, but that doesn't mean we're always going to be running stuff on GCP. It's not available everywhere. We do have clients in China and in Russia. And we do find in some certain cases that our clients may want to dictate the cloud provider to us. Some people we found are actually not happy running on GCP. And in those cases, we have to provide it in a different provider. So basically, we strive to be cloud portable, but we're not cloud agnostic. We want to be able to move our workloads across different clouds, and making a bet on open source technologies like Hadoop and Spark has been a driver of that. And our other big bet that we've made technically has been around Kubernetes as well. So adopting those open source technologies hopefully will allow us to move our workloads across different clouds in the future. And obviously the Anthos announcement a couple of days ago is going to be very interesting to us. All that said, we do use BigQuery for some things. I talked about how we use it for our billing data that drives the report that you saw a couple of slides back. We also have some direct-to-consumer offerings that we have as well. So we have a receipt scanning mobile app called WhoYou. It's only in the UK at the moment, but basically it provides loyalty rewards to customers who want to actually scan their receipts. And all the data for that gets stored in BigQuery as well. Because that's a direct consumer offering, it's essentially the client is dunnhumby ourselves, so we can host that wherever we want, and we choose to put that in BigQuery. So I want to talk a little bit about the solution architecture that we have within Core Technology. This is essentially the architecture that we deploy for each of our clients. So the base component is something we call network. That basically consists of a VPC network and cloud DNS. So we provision DNS A records and CNAME records for that client. On top of that, we deploy a component we call base. This provides an external proxy so that we can get to the outside world should we need to. An SSH gateway so that we as engineers can actually get onto the infrastructure itself should we need to for investigation, for maintenance, anything like that. And we also provide a single sign-on authentication proxy as well. And that's all part of our base component. On top of that, we have a component that we call Hive metastore. And this is what I was talking about a bit earlier in the talk, where we use Google's Cloud SQL offering to host the Hive metastore that will get used by our transient ephemeral clusters. So that is a component we deploy on its own. Essentially, it is a MySQL database running in Cloud SQL. On top of that, we have our data platform component, which is the thing I said I worked on. This is where we provide short-lived clusters to our data engineers. We do that through a combination of Dataproc, storage buckets, Airflow, and we also provide Jupyter instances to our data engineers as well. On top of that, our analyst platform that I talked about before, again, we're using transient clusters. We're using our auto-scale clusters using our Tidebell tool, and we provide Jupyter running on top of Kubernetes to our data scientists as well. We also run our various products on top of this as well. So that's our architecture. The way we actually deploy that is across two separate projects, two separate GCP projects. We have a project dedicated for hosting our runtime infrastructure and a project dedicated to hosting data, essentially, so state. So why do we do that? Well, it provides quite a lot of advantages, actually. So we could keep our long-lived state in a dedicated project and keep our short-lived runtime in a separate project. And really the key to this is segregation. So it's segregation of permissions around IAM, segregation of data retention, privacy policies, and it also makes it easier for disaster recovery as well. So essentially, we take the architecture that I showed you a couple of slides back, and we deploy that across those two projects that we dedicate per client. So essentially, we have multiple instances of this architecture running across our GCP estate. So why do we do it? Why do we have this single-tenant deployment model? Previously, when we ran everything on premises in our own data center, we didn't have a single tenant deployment model. We had very big clusters, and we shared them between multiple clients. Now we're in the cloud, we can use a single tenant deployment model. And the reason really is, it's one of segregation again, really. It's keeping things separate that don't need to be in the same place. It's a lot simpler for us to assign access for clients to actually access our infrastructure. We can control that with the natural boundary that a GCP project provides. It's a lot simpler for us to operate. We don't need to worry about using Kerberos or anything like that. Cost transparency is a big factor for us. If we want to actually see the cost of serving a particular client, it's very easy to do that because the billing data can all be grouped up to a particular project or a couple of projects. So we can see very easily the cost of actually serving a client, and you saw that on an earlier slide. The other big advantage that it provides is the ability to scale from zero. So what do I mean by that? If you think about how we work, we will sign a client to do some work for them. We'll provision two projects on their behalf. And at that point, there's essentially nothing in those projects. There's no data, there's no runtime components, and none of our data scientists or our data engineers will actually have access to it. So literally, at the start, we have nothing. It makes it a lot easier to scale that up as and when we need. We never had the capability to do that when we were on premises because we were using shared clusters. So we had to provision massive clusters in advance of actually signing our clients before we actually know that we were going to have them. So it makes it a lot easier for us to provide infrastructure to brand new clients. That's really the meat of the talk. I've been talking about transient clusters, auto-scale clusters, and the architecture that we use to provide that to our clients. Now, what I've done is provide a project on GitHub that really demonstrates a lot of how we do this. So what this is a project that will use Terraform code to deploy the parts of the architecture that I just demonstrated. And specifically, what it will do is deploy those transient clusters for us. So this is a screenshot from the README that's part of that project. Essentially, if you want to run this, all you need to do is clone the repo, run gcloud init, which will establish which project you actually want to, which GCP project you want to deploy this into. You enable a couple of services, specify the project. You have to create a cloud storage bucket, which is what Terraform will use to store its state. So Terraform needs to keep a record of what has been deployed. It does that in a storage bucket. And then there's a makefile in there which will actually show you how to, which will actually deploy this on your behalf. So you could clone that, create a project, run the apply. That whole thing should take about 5 minutes. I don't want to demo it today because we don't want to stare at a command line for about 5 minutes. But if you want to see how this works and how we set this up using Terraform, this is a really good way to do it. And when you finish, you could just run make destroy and it'll tear the whole thing down again. One thing you can do with Terraform is actually visualize all the components that it's going to deploy for you. And this is the output of running that Terraform graph command. The command in the bottom right-hand corner shows you exactly what command you need to run, which will generate this graph for you. And just to call out a few things on here, the yellow boxes are the network components that it will deploy for you. So we deploy a network, a subnetwork, and various firewalls that enable the different components to talk to each other. We deploy a Google storage bucket, which will actually store the data. That's the purple component that you can see at the bottom. The red components are the Hive metastore, so the Cloud SQL instance that is hosting the Hive metastore, and a SQL user that enables us to access that. The blue are the ephemeral clusters themselves, the transient clusters. This project will create 2 of them for you, both of them pointing at that shared Hive metastore, which really is the crux of this presentation, to be honest. And then on top of that, the green boxes are some jobs that we run on top of those clusters. And as I say, deploying this whole thing and running those jobs takes 4 or 5 minutes, and then you can tear it all down again afterwards. So it's a really good demonstration of how we do what we do and how you can use these ephemeral clusters using a shared Hive metastore. So before I came out here, I I said I work with a team of about 25, so I sent an email around to everybody I work with and said, like, can you just give me a grab bag of things I can talk about at the end, which will come under the banner of lessons learned. So here's a few things that my colleagues sent to me. I'm just going to go through them one by one. So this shared Hive metastore is great because it allows us to use these ephemeral clusters, but it does make upgrades very difficult because we got to coordinate teams of data scientists, teams of data engineers, and our infrastructure teams to make sure that we're not stepping on anybody's toes when we try to upgrade that stuff. We have to upgrade everything at the same time. We're working with Google to make that a little bit easier. We're hoping to anyway. But yeah, it is a bit of a pain point for us at the moment. We recommend that if you're going to do this, you peg Dataproc to a particular specific minor release. You don't have to do that. You can specify a particular Dataproc version, a major release version if you want, but we have seen that doing that, and then when we'll deploy the latest minor release for you, we have seen occasions where when the minor release changes, some of the scripts that we run, some of the initialization scripts do break. So be careful with that. Peg it to a minor release if you can. Stack driver logs can become very chatty, grow very quickly, and they can become very expensive. Stack driver is not cheap, certainly not if you're using a lot and you're throwing lots of logs into it. So use log exclusions within stack driver if you can, and configure your log4j properties so when it's not being too chatty. I said we're using Terraform, and we are. It's been great for us, but be aware that Terraform providers, the Google-specific Terraform provider generally lags what's available in the SDK. So you might be using features in gcloud, for example, that are currently not supported in Terraform. We've experienced that a few times, and we have made upstream commits to the Terraform Google provider, but it has been a bit of a pain for us. In shared clusters, users can easily crash the master nodes where driver runs on the master. So change the default deploy mode to cluster. If you're familiar with using Spark, you have two deployment modes, client and cluster. Where we have shared clusters, it's quite easy for one data scientist to run a nefarious job which actually brings the whole cluster to its knees. So for that reason, run with a deployment mode of cluster, and you minimize the chances of that happening. More lessons learned. Yarn application masters can fail if scheduled on preempted nodes. So I explained how preempted nodes are all about how Google could actually take that resource away from us. So running masters on that is not a good idea. You can get around this by using node labeling, and I believe there's also a Dataproc config option which has come out which prevents this from happening. So use that, and I can see Michaela in the back nodding as well. So happy to use that. The default Spark config in Dataproc can cause an individual to max out the cluster. Yes, so we're using these shared clusters. If you don't tune the initial configuration options, we were seeing particular jobs that our data scientists were running were actually bring clusters to the knees. So be careful with the default memory configuration that you apply to those jobs. Users need the Spark and Yarn UIs, but hard to make secure and available via our authentication proxy. Anyone that's used Spark will tell you that the Yarn and the Spark UIs are incredibly useful for diagnosing issues within those jobs, particularly if you've got skew in your Spark jobs. So we've had a lot of hassle making those UIs available via the single sign-on authentication proxy that we have. So something to be aware of. Make sure you get those working as early as possible. Conda is a useful tool for building consistent Python environments across Dataproc and Jupyter notebooks. So we need to make sure that the same Python libraries that we deploy to Dataproc are the same that we use in our Jupyter notebooks as well. Conda is a useful tool for doing that. And finally, GCS retention policies on temporary data sets. So we provide specific temporary areas, so Google storage buckets, that our data scientists can use for temporary storage. And you can set retention policies on those so that that data gets cleared down after a certain amount of time. We actually saw an occasion last week where the usage on one of our particular clients jumped from 17 terabytes to 36 terabytes overnight. And it was basically because one of our data scientists had dropped a load of data into one of these temporary staging areas. That happened on a Friday. by the end of Monday, that would automatically got cleaned up again because of the retention policy that we put on those temporary areas. Right, I am done. Thank you very much for attending, everybody. Ubiquitous slide about providing feedback if you could. I certainly really appreciate it. I've got about 10 minutes left, so if anybody wants to stick around, I'll take questions. And thank you once again for coming along. I hope it was useful.